On Valentine's Day 1982, a single particle passed through a Stanford basement laboratory. The chart recorder drew a perfect step. The lab was empty. What if a magnetic monopole, the particle Paul Dirac predicted in 1931 and humanity has searched for ever since, actually drifted through Stanford that night? What if the chart recorder drew exactly the line theory says a monopole would draw by accident, and 40 years of follow-up searches have been chasing nothing? What if the early grand unified theories of the 1970s were right and monopoles do exist, but the universe simply gave us one fingerprint and went silent? What does it mean for physics when an instrument working perfectly records exactly the signal it was built to find and then never repeats? Subscribe and follow along. We have the chart recorder paper, the original Physical Review Letters paper, and the 4 decades of search that came after. To understand why one event in a Stanford basement still matters today, we have to go back to 1931. To one of the strangest theoretical arguments in modern physics. Paul Dirac was 28 years old and already a leading figure in quantum theory. In a short paper that year titled simply Quantized Singularities in the Electromagnetic Field, he asked a question almost no one had bothered to ask before. Why is electric charge quantized? Why do we never see a particle with 1/3 of an electron charge or 1.5, but always integer multiples? Dirac showed that the existence of a single magnetic monopole anywhere in the universe would force every electric charge to come in fixed quantum units. One isolated north pole anywhere would explain a pattern we already saw in every laboratory. The argument was geometric, almost elegant in its inevitability, but Dirac himself was clear about what it did and did not prove. It did not prove monopoles exist. It said that if they exist, electric charge must be quantized, which it manifestly is. 40 years passed before the question came back, dressed in completely new theoretical clothing. By the early 1970s, particle physics had moved on to grand, unified theories, frameworks that combined the strong, weak, and electromagnetic forces into one bigger symmetry that broke apart in the very early universe. In 1974, Gerard 't Hooft and Alexander Polyakov independently showed that these unified theories did not merely allow monopoles, they required them. When the unified symmetry broke as the universe cooled, monopoles would have been left behind as topological defects, heavy, stable, isolated north and south poles with masses roughly 15 orders of magnitude larger than the proton. By the late 1970s, the abundance of these particles had become a problem. Standard cosmology predicted there should be far more of them than ordinary matter, enough to dominate the energy density of the universe. They were not being seen. Something somewhere was wrong. This is the climate Blas Cabrera was working in. Cabrera was an experimentalist at Stanford. He understood superconductors, and he understood what Dirac's quantization condition meant for a real measurement. A loop of superconducting wire kept very cold and very isolated supports a persistent current that does not decay. If a magnetic monopole flew through that loop, the current would jump by exactly 1 Dirac unit. The size of the jump is fixed. Either you see it exactly, or you don't. There is no ambiguous middle case. That is what makes the detector beautiful. A single event would be the single event. Cabrera built one. A 4-turn niobium loop about 5 centimeters across, inside a glass dewar of liquid helium, inside a superconducting magnetic shield. The signal was read out by a SQUID magnetometer. The data was logged on a slow chart recorder. On the 14th of February 1982 at 1:53 in the morning, the chart recorder drew a clean step. 8 units of flux quantum, the exact value predicted by Dirac 50 years earlier. Cabrera was not in the basement when it happened. The lab was running unattended. He arrived in the morning and noticed the step on the paper. He spent weeks ruling out the alternatives. Cosmic ray showers do not look like that. Mechanical jolts do not look like that. Power glitches and SQUID artifacts produced signatures the team had catalogued. None of them matched. The paper appeared in Physical Review Letters in May 1982. It is short. It is careful. It does not claim a monopole has been discovered. It reports an event consistent with one, and it invites the rest of the community to check. And then nothing happened. Cabrera ran the detector for years. He scaled it up by more than an order of magnitude in area. Other groups built their own detectors in Italy, Japan, and at Imperial College London. All of them looked. None of them saw a second event. The combined exposure across all the world's superconducting monopole detectors eventually exceeded the original Stanford run by factors of hundreds. The 1982 event remains unrepeated. It has also never been explained away. Reviews of the event conclude carefully that no plausible mundane source matches the signature. Modern searches have moved on to bigger ground. IceCube watches a cubic kilometre of Antarctic ice for the Cherenkov signature of a monopole crashing through it. The MoEDAL detector at the LHC looks for monopoles produced in proton collisions and stopped in plastic trapping volumes. Neither has seen one. The bounds on monopole flux through the Earth are now extraordinarily tight, ruling out almost all of the original grand unified theory expectations. What survives is a strange historical fact. On one specific night in one specific Stanford basement, a chart recorder drew exactly the line the theory said a monopole would draw, and the universe since then has been completely silent. Subscribe if you want more stories where the experiment came back with the answer and then refused to repeat it. The research is real. The lab notebook is real. The fingerprint is still there.